Hello guys, good morning to one of you. Can you hear me all? Okay, so what have we done last class? Could you tell me? I think we were doing chemical kinetics, right?
Yes, sir.
Okay. Where were we?
Order of the reaction.
What? Order. Okay. Okay. So, could you see the screen now?
Yes, sir. Yes,
Right.
sir.
Okay, so last class we have discussed about the rate of the reaction. We have also discussed the rate of reaction depends upon the stoichiometric coefficient of the reaction. If the reaction itself is not given, then we cannot find out the rate of the reaction. Correct? Because for different stoichiometric coefficient, the rate of the reaction will be different. Correct? We have seen one question also on this, the reaction of N2 and H2 gives NH3. Okay, one question on that we have discussed. We have seen that 3 different reactions gives 3 different rate of the reaction. Okay, so the answer for that question is cannot be determined. Hope you remember that. Okay, so rate of any individual species, any reactant or product is independent of the stoichiometric coefficient, and hence we can find out those rates if the reaction itself is not given, right? So rate of any individual species we can find out without its reaction, but for the rate of reaction we need the chemical reaction, right? So this must be given. We cannot assume the chemical reaction is this. Okay, all these things we have discussed. We have discussed few numericals also onto that. Now there's a rate law, right? Rate law, which is reduced from the law which we call it as law of mass action. Okay, so based on that, because sometimes actually what happens initially for any reaction, I'll take this example and make you understand this particular concept. Okay, for a reaction, say AA plus BB, it gives some product. Okay, suppose the reaction is this we have. Now for this reaction, if you write down the rate expression, okay, so rate expression for this reaction, we say rate is directly proportional to the active mass of reactant species A and B. Active mass you can consider as concentration only, right? But the actual term that we have, there is a bit difference between concentration and active mass, right? But that is not required here. Okay, here we consider active mass and concentration term same, right? But the statement, if you write, we do not use the term concentration over there. Instead, we'll use what? We'll use active masses, not concentration. Okay, so this active mass, okay, to the power its stoichiometric coefficient, which is A and B. This law, the law which has given this particular relation of rate with the active mass of A and B, this is the active mass. Okay, this expression, rate with this active mass of A and B to the power the stoichiometric coefficient of the reaction, this relation we call it as law of mass action. Law of mass action. But this relation was not found to be correct for all the reactions. Okay, so there are actually, if you see the reaction, classification of reaction, so based on the number of steps involved, right? Number of steps involved in the reaction, there are actually two types of reaction we have. Okay, based on the number of steps involved, the reaction is classified into two categories. The first one is elementary reaction, and the second one is non-elementary. Non-elementary reaction, we also call it as complex reaction. Complex reaction. Elementary reaction is simple reaction, not complex. These are simple reaction. So we can also understand this, we also call it as one-step reaction. Those reactions which finishes or which gets complete in one single step are called elementary reaction. Complex reaction, non-elementary reaction, more than one step. Series of steps we have into this. Okay. So this relation, the law of mass action, is true only for elementary reaction. This relation that we have written over here, rate is equals to this, it is true only for elementary reaction, not for non-elementary reaction. Okay. So obviously this relation of rate we cannot use for all the reaction because it is not valid. Okay. So then what happens? We have given a new rate law, just a small change into this, and we have given a new rate law over here. Now, when you a little bit when you generalize this, we'll discuss that also once. So we have given a new rate law, and that rate law is what you write it down. Write down the statement of this new rate law. It is based upon the law of mass action only. Just one change into that. Okay, write down the rate of a chemical reaction. The rate of a chemical reaction is directly proportional to of a chemical reaction is directly proportional to the concentration of the active masses of the reacting species active masses of the reacting species, comma, raised to a suitable power which may or may not be equal to, which may or may not be equal to their respective stoichiometric coefficient. Which may or may not be equal to their respective stoichiometric coefficient. Finished? I'll repeat it once. The rate of a chemical reaction is directly proportional to the active masses of the reacting species raised to a suitable power, which may or may not be equal to their respective stoichiometric coefficient. Okay. So for the same reaction that we have taken just now, for the same reaction, if I write down the reaction AA plus B gives product. For this reaction, if I write down the rate expression, that is rate of this reaction is directly proportional to the active mass of A and B, product of A and B, to the power any number x and y. Okay. This x may be equal to A, y may be equal to B. So it is maybe, may not be. So when x is equals to A, y equals to B, the reaction, this is true for the elementary reaction. It means the reaction is elementary reaction. So basically, if the reaction is elementary, then we can write here A to the power A, B to the power B, like we have written in the previous slide. But if the reaction is non-elementary, more than one steps involved, right? Suppose we have 3 simple steps into that, right? Then this rate expression will write down with the slowest step among the 3, right? So in that case, this x and y may not be equals to A and B respectively, right? Rate of the reaction we always defines with the slowest step of the reaction. If the reaction involves more than one step, then the slowest step that is there, with that only we'll write down this rate expression. Okay, so this is just a slight change in the law of mass action, which suggests that rate is directly proportional to the active masses of the reacting species raised to a power which is equal to their respective stoichiometric coefficient. Means x and y, if you replace this by respectively A and B, then that is law of mass action. But that law of mass action is not true for non-elementary reactions. We have done this change over here. And what is the change? The power of x, A and B may or may not be equals to their respective stoichiometric coefficient. So this is the new rate law, and it is true for all type of reaction, whether it is elementary or non-elementary. Now this x and y are the experimental value. This is very important. So all of you write down this. This x and y here are determined experimentally. Okay, so by looking at the reaction, we cannot find out the x and y. These are experimental value. So if this rate expression is not given with the value of x and y, we cannot find out this. This should be given in the question experimentally, right? Because x and y are the experimental value. There's no theoretical way by which we can find out x and y of any reaction. Okay. Now, if I remove this proportionality sign, the rate becomes rate is equals to the rate constant K, concentration of A to the power X, concentration of B to the power Y. Again, I am telling you, these are the actual term here we use is active masses. But like I said, there is a small difference between active mass and concentration. So we are taking concentration only here. So like after this, we'll use the term concentration only. But when I have to write down the expression of this, what is new rate law, then please do not write concentration term over here, but you write active masses. But to use to solve questions, we'll use concentration only. So concentration of A to the power X, concentration of B to the power Y. Okay. Now there is a term that we define here that we call it as order of the reaction. Wait a second, order we'll discuss after some time. One more thing we have to see here. What is this K here? The K is the rate constant of the reaction, or we also call it as velocity constant. Velocity constant, or it is also known as specific rate of the reaction. Why it is a specific rate, that also you can understand. Write down. The rate constant K defines as write down. The rate constant K defines as the rate constant K defines as the rate of the reaction defines as the rate of the reaction when the concentration of all the species involved in a concentration of all the species involved in the rate law expression involved in the rate law expression is taken as unity 1. The concentration of all the species involved in a rate law expression is taken as unity. So you see what happens, the rate law expression is this, correct? When the concentration of A and B, if you take it as 1, then rate is nothing but the rate constant, right? So with unit concentration, rate constant becomes the rate of the reaction, and hence it is the specific rate of the reaction. At a specific value of concentration, K becomes the rate of the reaction, and that specific value is what? Unit concentration, that is 1, right? Now the other thing is the unit of the rate constant K. What is the unit of a rate constant K? This is very important. Okay, I'll tell you how they frame questions over this. First of all, you see the rate law expression that we have here, right? So with respect to these powers, that is X and Y, we define a term and that we call it as order of the reaction, and order is represented by N. N is not number of moles here, it is the order of reaction. Okay, so write down the definition, order. it is the sum of the power. It is the sum of the powers of the reacting species. It is the sum of the power of the reacting species in a rate law expression. In a rate law expression. Okay. So if the rate law expression is given as, for example, I am taking some random expression here. If the rate law expression is given as R is equals to rate is equals to the rate constant K, A to the power X, B to the power Y, and C to the power Z, and so on, like this, suppose we have. Then the order of the reaction, that is N, is equals to sum of the power of the reacting species involved in the rate law expression. N is equals to X plus Y plus Z, correct? And if any other component we have, then we can add those values also. So this is the order of the reaction. Since X, Y, and Z, like I said, this X, Y are determined experimentally. So this N is also, it is the experimental value. Experimental value. Order is an experimental quantity. We cannot define it. We cannot find out it. Okay. It is an experimental quantity. Right. It can be fractional also. It can be fractional. It can be zero. Even it can be negative also. Negative with respect to one species involved. Okay. Overall order could not be negative. Okay. But with respect to one species, it can be negative. Right. Generally, overall order is not negative. That is not possible. If it is there, it means the reaction is extremely complex reaction. Okay, but that is not our a concern. It is not our portions also in the syllabus, right? So order is an experimental value, right? It can be zero, it can be fractional, it can be negative also with respect to one species. Okay. Overall order can be zero or fractional, but negative is very difficult. Okay. Now we have to find out the unit of K, right? So you see this, how do we find out the unit of K? Left hand side we have rate. So if you substitute all the units over here, so rate is what? Concentration by time. So rate we can write mole per liter second. That is the unit of rate on the left hand side, is equals to the rate constant K. A, B, C are what? A, B, C are nothing but mole per liter. Those are concentration only, mole per liter. So this, all these, if you write down mole per liter to the power X, mole per liter to the power Y, mole per liter to the Z, and so on, that will be mole per liter to the power X plus Y plus Z, right? So this expression further, it becomes mole per liter second inverse is equals to K into mole per liter to the power N, where N is the order of the reaction, right? Now simply if you solve this, you'll get K is equals to, the unit of K is mole per liter to the power 1 minus N second, or better if I write down time here, that would be a better word to write here, because the unit of time can be anything. It can be minute, hour, anything. So I'll use the term time only here. So here also we have time inverse. Here also we have time inverse. Can be anything. Okay. So this is the unit of K. Okay. So did you understand this? Any doubt till here?
No, sir.
No. It's clear? So you see the value of the unit of K depends upon the order of the reaction. It is not a fixed unit, right? Depending upon the order of the reaction, the unit will change, correct? So with the help of the unit of K given in the question, we can actually find out the order of the reaction, correct? Sometimes like in the coming this thing, we'll see now only that for different order, we have different relation of time and concentration, right? So for any calculation, time and concentration, any calculation of the concentration of reacting species after this time, 10 minutes, 15 minutes, like that. For any concentration, right, we need to know the order of the reaction. For any kind, those kind of calculation, we need to know the order of the reaction. Sometimes what happens in the question, they won't mention the order, but they'll mention the unit of K. So with the help of unit of K, we can find out the order of the reaction. Right down here. With the unit of K, unit of K, rate constant, we can find out the order of reaction. For example, if n is equals to 0, 1 and 2, we can find out this value, right? So for n is equals to 0, you see the value of K, the order of K is, the unit of K is mole per liter time inverse. This is the order, n is equals to 1. The unit of K is only time inverse. N is equals to 2. Unit of K is mole per liter to the power -1 time inverse. So if the question is given with any of these units, then correspondingly we can find out the order of the reaction. We'll have the idea of the order of the reaction. Correct? Any doubt in this? No? That's why the unit of K is very important. Okay, we can find out the order or determine the order of the reaction with respect to the unit of this. Okay, now we'll discuss the kinetics of various order reactions. Write down the heading. Various order reaction. So first we are talking about zero order reaction. The important one is zero order and first order. These two are important. Okay. So you see, for a reaction, say write down the definition here first. These are the reactions whose rate, these are the reactions whose rate is not affected by the concentration of whose rate is not affected by the concentration of the reacting species. Okay, reacting species. Now the examples of zero order reaction we have, actually all photochemical reactions are zero order reactions. Means in presence of light, whatever reaction is taking place are zero order reaction. Okay, so for example, we have H2 plus Cl2 gives 2HCl. This is a photochemical reaction because it is taking place in presence of light. Okay, some heterogeneous adsorption reaction if you have. Okay, for example, the decomposition of NH3 in presence of molybdenum catalyst into N2 plus 3H2. This is heterogeneous adsorption. Okay, some examples you must keep in mind. That's why I'm giving you all this. Okay, enzyme catalyst reaction, enzyme catalyzed reaction are also zero order reaction. Okay, enzyme catalyze all those reactions in which enzyme is behaving as a catalyst. Okay, now you see, to find out the relation of it, the concentration and time relation, right? What we can write, suppose a reaction I'm assuming, and that reaction is a zero order reaction, A gives product. This is a reaction I am assuming. Okay, so the rate of this reaction, what we can write, rate is equals to minus of d by dt of concentration A. This expression we have already seen. Rate of A is minus of dA by dt. That is what I have written. This is equals to, with the help of the new rate law, law of mass action or the new rate law, we can write K concentration of A to the power the order of the reaction, right? So what should be the power of A here? Could you tell me?
N. N.
What?
N.
The power
N.
of A should be the order of the reaction, which is 0,
0.
right? Now you see this expression becomes the rate minus dA by dt is equals to the concentration, sorry, the rate constant K, and anything to the power 0 is 1, right? This K is a constant. K is a constant. So rate is what? Rate is also constant. That's why you see the rate of this reaction is independent of the concentration of the reacting species. Correct? Rate is independent of the concentration of the reacting species. Now just you need to solve this differential equation to get the expression of concentration and time. Okay? So when you solve this on the reacting species, this equation, differential equation, minus of dA is equals to K dt. Okay, so you must have done little bit of integration, and that you can apply here, and you can easily solve this differential equation. T is equals to 0. The initial concentration I am assuming as A naught. T is equals to T. The concentration I am assuming as AT. No doubt in this. So this is the limit of this integration. No doubt in this. Please respond, guys.
No, sir.
No, sir.
Okay. Right. Now, when you solve this, what you'll get, see, you'll get concentration of A at any time T is equals to concentration initially minus KT. This is the relation of concentration and time for zero order reaction. Similar method we have to use to find out the concentration and time relation for other different orders reaction like first order, second order. Correct? So suppose if you know the value of A, right? Know the value of this A naught, initial concentration, you know, K is given. So after any time T, you can find out the concentration which is left here. This AT is the concentration left because A is converting into product. So concentration of A is continuously decreasing, right? So AT concentration is the concentration of A which is left at time T. Understood, guys? Okay. This graph is rate versus the time. Okay. This graph is the concentration versus time. Concentration means concentration of product, sorry, reactant. Okay. So now when you look at this graph, the rate and time, rate is independent of time, right? Rate is constant basically. You look at this, the expression we have, rate is equals to what we have? Rate is equals to K into A to the power 0, correct? So it is 1, K is a constant, so rate is nothing but a constant. It does not change with time, right? Hence, the graph that we get here will be a straight line parallel to the x-axis like this. Whatever the rate we have, that rate will be constant throughout. Are you getting it, guys? The rate won't decrease or increase, won't decrease with time. The reaction goes with a constant rate. Okay. Now, since the reaction goes with a constant rate, so this is the only reaction, zero order reaction, which goes for 100% completion. 100% completion we can observe over here. But in all other order reaction, like first order and second order, rate decreases with time. Rate of the reaction decreases with time. So around 98% of the completion, the rate becomes extremely slow. The reaction becomes extremely slow, and hence we assume that the reaction is over. right? However, the 100% completion is not there, right? So the first order reaction is the only reaction which goes to 100% completion since it is moving with a constant rate, right? And hence it will complete. The concentration of reactant with time, with this equation, the graph we can draw and we'll get a straight line, something like this. This is the graph we have. With this, y is equals to mx plus c, you can assume, right? So this is the graph we get. Now this point is the x coordinate we have, and the coordinate of this point we can write it as concentration At is equals to 0. At this point, you see the concentration of reactant is 0. So when you put At is equals to 0, the time will be A naught by K. Okay. So this axis is the coordinate of this point is A naught by K, comma 0. This is the coordinate of this point. Okay. Now this coordinate of this point is what? At 0 time, the concentration is A naught. So the coordinate of this point is time 0 concentration A naught. So this is a 2 coordinate we have. If this graph is given, so this distance from this point to this point is nothing but the initial concentration. See, A naught like this, you always take this as initial concentration. This actually means the concentration at time t, this is the concentration at time 0. That's why it is the initial concentration. Any doubt in this? No? Okay.
No.
Could you tell me the graph over here? I'm just drawing a small graph. So x-axis I am taking is the time. And this is the concentration of product. Could you tell me this graph?
Increases.
Increases linearly.
From the origin, right? Is it right, guys?
Yes, sir.
Okay. So one important observation of zero order reaction is what? I write down here at time t is equals to 0. You see this side we have time, and this side we have concentration of reactant. So square bracket reactant means concentration of reactant. At time t is equals to 0, the concentration of reactant is A naught. At time t is equals to t, the concentration of reactant is what? A naught minus Kt. At time t is equals to 2t, the concentration of reactant is A naught minus 2Kt. At time t is equals to 3t, the concentration of reactant is A naught minus 3Kt. Is it clear? Okay. Now, when you look at this, this concentration here, the difference or the common difference that you are getting here is nothing but Kt. Means the difference in concentration in this time is Kt. In this time, it is also Kt. And in this time, it is also Kt. Means at equal time interval, the change in concentration is same, correct? Right? So what we can say, you see, this is the pattern of AP, arithmetic progression. Yes or no, guys?
Yes, sir.
Correct. So what we can say, write down this point here, note down this point, that the concentration of reactant, react in equal time interval is the key, right? The concentration of reactant reacts in equal time interval follows the pattern of AP, arithmetic progression. Right. Means what is the meaning of this? In equal time, the equal amount will react. Write down. Write down this point. For write down like this. For a given time period, the amount of reactant reacts the amount of sorry what for a given time period the amount of reactant react is equal, right? And it is independent of the initial concentration. Done. Okay. Now you see the application of this, you will get this question in the exam definitely, right? And mathematically also you can say solve this by equation, okay? But that is not required. You can do this directly without putting your pen down, okay? You can solve at your fingertip easily. We are trying to use this method, okay? So you see here, first of all, what happens? Suppose I am giving you a reaction, and for that reaction, zero order reaction, and suppose 100 concentration to 90. For this conversion, suppose the time taken is 10 minutes. I'm just taking one random example. So in 10 minutes, what happens? From 100 to 90, the change is there. Okay. So what is the difference? What is the amount react? 10, right? 100 minus 90. 100 was initially present, and here we have 90 present now at time t is equals to 10 minutes. So 10 concentration has been reacted, right? Suppose this data is given that 100 to 90 conversion in 10 minutes. Then what is the amount react for the same time if the initial concentration is 50? So what is this amount for the same reaction when time t is equals to 10 minutes? Are you getting it?
40.
Right? So answer will be what? the answer will be 40. Means the concentration that is left here is 40. You can do this by method. Okay, answer will be this. We can do this by method because we know this relation. AT is equals to A naught minus KT. So A naught is 100, AT is 90, K we have to find out, and T is 10. So from this we'll find out K, and since we have the same reaction, so this K we can substitute here. Now for this AT we need to find out. So AT is equals to what we can write for this reaction, right? Means the reaction is same, only the initial concentration is different here. We are taking 100 and here we are taking 50. Right, so AT is equals to A naught is 50 minus this K will substitute over here and time is 10. So in this way we can find out AT, that would be the answer over here for this question. But what I'm telling you, you don't have to do all this stuff, okay? However, this calculation you you may find it very easy, but you won't get this kind of easier calculation in the exam, right? So I'm telling you to avoid all this calculation. Don't do all this. That is not required because we know the fact that the amount reacted in zero order reaction follows the pattern that is AP, arithmetic progression. So whatever the change in concentration we have in 10 minutes, that should be the same change we have here also in 10 minutes, whatever the initial concentration you take. So here the change is 10. So it means 50 to 40 if you have to go, again it requires 10 minutes. If you have 60, so 60 to 50 if you have to go, again the time required is 10 minutes. Okay. So anything they can ask you in this. Right. So in equal time interval, equal amount reacts in a zero order reaction. Did you understand this? No doubt. Yes. Correct. Okay. So this property, this AP, this property is very important. You can save your time by this method. Must keep that in mind. Zero order and first order are very important. You must keep this in mind. Okay. So this is we have done. Now one more thing here. This amount here, this amount is the amount of product forms. This one. It is the amount of product. Because this is the amount reacted, correct? And by this amount, the concentration of reactant decreases. It means this converts into product. So concentration of product, if I write down, the concentration of product is nothing but K into T, right? That's why the graph here you see, the previous one, here you see this graph. The graph is a linear graph and passing through origin. X is the concentration of product is equals to K into T. X and T. So X, T, Y is equals to MX form we have passing through origin. No doubt. Can I move on?
Yes, sir.
Okay. Next, write down first order reaction. Now everything is same, like the pattern is same to find out the relation here. The first order reaction, suppose I am assuming the reaction is A gives product. A gives product. Its rate of the reaction is minus of D concentration of A by dt. See, I'm using the same pattern, exactly same pattern, is equals to K concentration of A to the power 1. Okay, now just you need to solve this differential equation to get the relation of A and T. So concentration of dA by concentration of A is equals to K dt. And when you solve this, you'll get K is equals to 1 by T ln of A naught by AT. I forgot to calculate one simple thing here. I'll tell you what it is. See, when you have this relation, right? So if I ask you, what is the T half for a zero order reaction? So at T is equals to T half, what we can write, I'll just finish this off, just a second. At T is equals to T half, what is the concentration we have? So at T is equals to T half, what we can write? A naught AT is equals to what we can write? A naught by 2. 50% reaction is there, no? Right? Do you understand this? Can we write down this? AT is equals to A naught by 2. What is T half? T half is the time required for 50% completion of the reaction. Last class we have discussed this definition. Okay, T half is the time required for 50% completion of the reaction. So when T is equals to T half, AT is equals to what? A naught by 2. So when you substitute this 2 in this equation, you will get AT is equals to A naught by 2. So when you solve this, you get T half expression for zero order reaction is equals to, could you tell me? A naught minus A naught by 2. So we can write T half is equals to A naught by 2. This is the formula of T half for zero order reaction. Write down this formula. Clear? So this is the relation of log and time for first order reaction. Correct. Okay. Now you must keep in mind, AT is the amount of reactant left always. Amount of reactant left at time T. It is not the amount which reacts. It is the amount of reactant left at time T. Correct? Could you tell me the formula of T half for first order reaction? What is the formula for T half for first order reaction? See what we can write here, that at time T is equals to what is AT? A naught by 2. So we can substitute this in the above relation. So K is equals to 1 by T half ln of A naught divided by A naught by 2, right? So T half is equals to ln of 2 by K, which is nothing but 0.693 by K. Copy down this. Are you done? Okay, right. Now, you see this relation. From this relation, what we can conclude that we try to understand. See, what we can write ln of, just a second. What we can write here, the ln of A naught by AT is equals to K into T. So A naught by AT is equals to what? E to the power KT, and hence AT is equals to A naught e to the power minus KT. Right? This is the relation we have. Concentration at any time T is initial concentration into e to the power minus KT. Okay. Now you tell me one thing. At time T is equals to 0, what is the concentration we have? A naught. At time T is equals to T, what is the concentration we have? A naught to the power e to the power minus KT. At time T is equals to 2T, the concentration is A naught e to the power minus 2KT. T is equals to 3T. The concentration is A naught e to the power minus 3KT. This is the concentration we are getting. Okay. Now, if you find out the ratio of the two at the consecutive time interval, equal time interval, the ratio of this is equals to, right, this by this is e to the power KT. Even here also, the ratio is e to the power KT. And here also, the ratio is e to the power kt. Means at equal time interval, we have what? We have equal ratio of the product from t to 0 to t to 2t, and 2t to 3t. The ratio of the amount of product forms or the amount of reactant left, okay, that is same. It means what we can say, write down here, note down this point. The concentration of the reactant left, the concentration of the reactant left at equal time interval forms GP, geometric progression. Write down. Second point to write down into this. In equal time interval, this is for first order. In equal time interval, equal percentage of reactant reacts. Remember, in zero order, we have in equal time interval, equal amount react. Here we have equal percentage of the reactant reacts. Right? This means what? Suppose from 100 to 90, you've gone in 10 seconds. Then what is the concentration we get after 10 seconds if the initial concentration is 70? 72, what concentration we have here at time t is equals to 10 seconds? Could you tell me?
60.
Is it 60?
Yes, sir.
60, right? 60.
60.
Yeah. All of you are getting 60?
Yes, sir.
Yes, sir.
Okay. See, what I said here, the answer is not 60 for this. The answer is 63. Okay. Now you must be thinking how I'm very sure with this value 63. And you can do this on your fingertip. What I said, that equal percentage react in this equal time interval, right? First order, equal percentage reacts. Answer will be 60 if the order is 0. Right, there we have equal amount react. Okay, here we have equal percentage. So what is the percentage react here in 10 seconds?
90%.
10%. So again, in further 10 seconds, 10% only reacts. Like from 90 to, if you consider 10 more second over here, the concentration will be 81 then. Further 10% react. Further, if you see, after this, if you have again 10 seconds, then again 10% of 81 reacts and rest is left. So if the concentration is 70, for equal time interval, we know equal percentage react. So here if it is 10%, so here also 10% react. And hence 63 is the concentration left. Did you understand this?
Yes, sir.
Okay. So in first order, we have equal percentage. In zero order, we have equal amount reacts. No doubt. Or example of first order you did not write. Write down the example of first order reaction. First one. Write down decomposition reaction. First order reaction. For example, 2N2O5 gas converts into 2N2O4 gas plus O2. Yes. Right. Second example we have radioactivity. The reaction related to radioactivity are first order reactions. Third, growth and decay of bacteria. Decay of bacteria. Okay. Inversion of cane sugar, also first order. Inversion of cane sugar. All these are first order reaction. Second order reaction. Again, this is the similar way we'll do. So I'll do this quickly. Suppose A gives product. So its rate expression would be minus D concentration of A by dt, and that will be equals to K concentration of A to the power 2. Right? Similarly, we have to solve this second order differential equation. It's minus of dA by dt. So A square is here, minus of K dt. Then you integrate this 0 to t. When time is 0, concentration of A is A naught. When time is t, concentration of A is AT. Okay, so now when you solve this, you'll get K is equals to 1 by T, 1 by AT minus 1 by A naught. Could you tell me the expression of T half? What is the expression of T half? What happens at T half? AT becomes A naught by 2. So you substitute over there and tell me the expression of T half. What happened?
K is equal to 1 divided by T into A naught.
1 divided by 2 into A naught, right? Yeah. So when you substitute AT is equals to A naught by 2, so we can write down at T is equals to T half. AT is equals to A naught by 2. Disha, any doubt?
No, sir.
Okay. So when we substitute these two values here, we'll get K is equals to 1 by T half 2 by A naught minus 1 by A naught. So that will be T half is equals to 1 by K into A naught. Okay, so one observation is very important here for all the three reactions because they ask questions T half related question, right? So for n is equals to 0, T half is equals to what? If you see, it is A naught by 2K. N is equals to 1, T half is equals to 0.693 by K. N is equals to 2, T half just now we have calculated 1 by K into A naught. Correct? So now you see, for zero order reaction, T half and A naught is directly proportional. Means more initial concentration, more will be the T half of the reaction. Right? More initial concentration, more will be the T half of the reaction. Right? T half is independent of initial concentration. Initial concentration means whatever initial concentration you take, T half won't change, right? The reaction will be at half of its concentration at that particular T half value. Okay, here T half is inversely proportional to the initial concentration. Means what? More initial concentration, lesser will be the T half. Right? Reaction rate is more over here basically. Clear? Second order reaction, you write down the example. Saponification reaction is a second order reaction. Means what? It is the reaction of ester with base, NaOH. So it forms CS3COONA, salt of this ester, plus an alcohol. Saponification reaction. Second one, decomposition of NO2. Third one is conversion of ozone into oxygen. This. Copy down this. Okay. Now we solve some questions on this. Okay. See this question. I'll write down here. Starting with 1 mole of a compound A, what is that, Kirtana? Any doubt?
No, sir.
Okay, fine. Look at this question. Starting with, write down the question first. One mole of a compound A. It is found that the reaction is 3/4 completed in 1 hour. Calculate the rate constant. Rate constant if the reaction is of first question, first order, and second order. Try this. Done? Okay, see, how do we do this? Starting with 1 mole of a compound A, right? So first of all, the order we have to assume first order, n is equals to 1 we have. So we know the relation of concentration and time for first order reaction. And what is that relation? The relation is
Concentration.
AT is equals to, or in terms of log, if I write down, that would be K is equals to 1 by T log of what? A naught by AT. Okay. Since you have taken here logs, this one should be 2.303. Otherwise, you can take ln. Okay, this should be 2.303. Now, what all values given over here? A naught is given 1. Reaction is 3 by 4 completed. Means AT is what? 1 minus 3 by 4. That is 1 by 4. Okay, T is equals to 1 R. All these, if you substitute here, you'll okay, simply 2.303 by 1 log of A naught by AT is 4. So when you solve this, you will get what? 2 log 2. So 2 log 2 is 0.30, into 2 is 0.6. So 2.303 into 0.6. So this approximately you will get 1.38 something, right? Now, could you tell me the unit of K over here? What is the unit of K? See, this is concentration term gets cancelled. Time is in R, so it is per. Or what you can do, we have already done the unit of K with respect to the this thing, the order, right? I'll show you just now, wait. So this is here. You see this. If order is 1, what is the value of K? Time inverse. Time is given in R in the question. So it is R inverse. So with the help of this, you can say, or if you do not remember this, then you should do this directly over here. A naught, this term is unitless. Time is in R, so it is R inverse. Could you find out this for n is equals to 2? What we have in the second case, n is equals to 2. So what is the relation of K and A we have? K is equals to 1 by T into what we have? Tell me the relation. Just that relation, you have to substitute the value. And the relation is what?
1 by
AT minus 1 by A naught. 1 by AT minus 1 by A naught. So what all values given here you see? Again, A naught is equals to 1, AT is equals to 1 by 4, time is equals to 1 hour. So if you substitute here 1 by 1 into 1 by AT is 4 and 1 by A naught is 1. So that would be 3. So it is 3. Could you tell me the unit over here?
Mole per liter inverse into time
hour
unit.
inverse
Mole per liter inverse.
into hour inverse.
Is it mole per liter or liter per mole? Acha, mole per liter inverse you are saying, and then it's fine. Mole per liter inverse hour inverse.
Inverse.
Correct? So this is the answer.
Yes,
For this. Correct?
Yes, sir.
Okay. So basically these relations you need to know and then you have to substitute the value. This question you see, one more easy one. Half-life related questions are important. Okay. The half-life periods of a reaction write on the question half-life period of a reaction at initial concentration at initial concentration 0.1 mole per liter and 0.5 mole per liter are 200 seconds and 40 seconds respectively. It's given. You need to find out the order of the reaction. Is options are also given. I'll write down the options. It is 1, it is half, 2, 0. Try this. second order. Okay. Is it second order you are getting? Yes, second order is correct. Okay. See, how do we do this question? First of all, what you can see, if initial concentration is 0.1, correct? See here, A naught is 0.1 molar. So T half is 200 seconds. If A naught is 0.5 molar, T half is 40 seconds. That is what is given. Means if A naught increases, T half decreases. Then what we can say? T half is inversely proportional to A naught. This is what we can conclude from the given data, that at T half decreases when A naught increases, it means T half and A naught are inversely proportional. And this is the only relation we have in we can write this for second order reaction. The three order that we have done 0, 1 and 2, in this three order you see, the second order is the only one in which T half and A naught are inversely proportional. Clear, guys? Any doubt? No? Okay. This is one thing. One more relation I'll give you here, okay, which you should memorize, okay. On the basis of that also you can solve the question, okay. T half for any reaction, it is directly proportional to the initial concentration of reactant to the power 1 minus n, where n is the order of the reaction. It is always true. Whatever order we have, it is always true. Okay. So now for this one, what we can write, if by this method, if you do, you see how we can solve this question. Suppose T half 1 divided by T half 2, because we have two different T half values, is equals to what we can write, A naught 1 divided by A naught 2. This whole thing to the power of 1 minus n. Now we'll substitute all the values here. You see T half 1 is what? 200 by 40. This is equals to 0.1 by 0.5, sorry. 0.1 by 0.5. You see what we are getting? This is 5 and this is 1 by 5 to the power 1 minus n. So when you solve this, 5 to the power 1 is equals to, we can write 5 to the power n minus 1. So further, what we can write, 1 is equals to n minus 1 and hence n is equals to 2. By this method also you can solve this, okay, mathematically. So this relation is also very important, right? I would suggest all of you to keep this relation in mind. Even we can derive this also by assuming the nth order reaction, right? We can derive this also, but that derivation is not important. You must know the relation of half, T half and the order of the reaction. Correct? Understood? No doubt?
No, sir.
Okay. Now, the next thing we have to discuss is factor affecting. Write down the factor affecting the rate of a reaction. Factors affecting the rate of a reaction. Okay, the first factor we have the concentration of the reacting species. Reacting species. Write down. Write down. As concentration decreases, the rate of the reaction decreases. Because lesser concentration, lesser will be the tendency for the reaction to go in forward direction, right? As concentration decreases, rate of the reaction also decreases. Correct? Okay. In this only you write down the concentration of the reacting species is maximum at time t is equals to 0. At time t is equals to 0 means the initial condition. Means at this point of time, the rate of the reaction is maximum. The rate of the reaction is maximum. Okay. Now, next to write down nature of reactant and product. The second one. Nature of reactant and product. Write down the rate of the reaction. The rate of the reaction depends upon the types of bond the rate of the reaction depends upon the types of the bonds broken or formed types of the bond broken or formed during the process of a reaction, and also the number of such bond involved. Okay, basically, see, the chemical reaction is nothing but the bond making and bond breaking process. If the strong bond you are breaking, it means the rate of the reaction will be low. For weak bond, you can break those bonds easily and new bond can form, it means the rate of the reaction will be fast. The reaction converts into the product with a faster rate. So what types of bonds are involved, that also affects the rate of the reaction, okay? So that is what the nature of reactant and product, what kind of reactant and product we have here. So basically, if I give you an example here, this example you must remember, the reaction of NO with O2 gives 2NO2. Reaction of carbon monoxide with O2, it gives 2CO2. It looks very similar reaction, right? But the first reaction, this one, is fast and the second reaction is slow. It's very fast reaction and it is a slow reaction, right? So it depends upon that what bond is about to form and what bond is about to break. Here the carbon oxygen bond can form easily than nitrogen oxygen bond, and hence, sorry, other way. Nitrogen oxygen bond forms easily than the carbon oxygen bond, and hence this reaction proceeds with a faster rate in comparison to the second reaction. Okay. The third factor we have is the presence of catalyst. This one is also important. Write down. Catalyst also affects the rate of the reaction. Also affects the rate of the reaction by changing the activation energy of the reaction. By changing the activation energy of reaction. Okay, catalysts actually also have two types. Okay, this catalyst, we have two categories into this. One is positive catalyst and other one is negative catalyst. Mainly we deals with positive catalyst. Okay, if nothing is mentioned, it means we have to take the positive catalyst. Okay, so we always assume positive catalyst if it is not mentioned, right? Unless it is not mentioned. Okay, so positive catalyst, what it does, it actually decreases the activation energy of the reaction. Write down here, it decreases activation energy. EA is the activation energy. We will see this also, right? Activation energy, and hence increases the rate of the reaction. Rate of reaction. Less activation energy, faster will be the rate. That is what the relation we have. We'll discuss this activation energy in this temperature relation. We'll see that later. Okay. Negative catalyst actually decreases the rate of reaction by enhancing the activation energy of the reaction. So more activation energy, lesser will be the rate of reaction. That is what the effect of catalyst. Okay, when we do temperature, we'll discuss a graph of it. Okay, and activation energy we'll try to understand over there only. Okay, the other factor we have, the fourth one, write down the surface area of reactant. Surface area of reactants. Write down, the larger the surface area, faster will be the rate of reaction. Larger the surface area, faster will be the rate of reaction. See, what does it mean? Reactions reactions are nothing but the collision among the reactant molecules. Collision of molecules. Right? So collision actually, when collision takes place between the two atoms, right? So when they comes into the contact of each other during collision, right? So the surface area is a factor over here, this surface area, where they are colliding with each other. So if this surface area is more, then the rate of reaction is more. We'll have a better collision there, and the chances of the reactant to convert into product will be more. So surface area is what the area with which the two reactant molecules collides, right? More surface area, better collision it is, more like better collision, chances are high to get the product in that reaction. So surface area is also a factor. Now the fifth factor is presence of light. Presence of light is a factor we have in photochemical reactions, where those reactions which takes place in presence of light, mainly the reactions which involves free radical mechanism. Okay, so write down, light affects those reactions light affects the rate of those reactions. Write down, light affects the rate of those reactions where the bond dissociation is possible, with the energy of photons. With the energy of photons. Okay, so basically what happens, for example, when we have a reaction like H2 and Cl2, which gives 2HCl, so in presence of light, this reaction is very rapid. Okay, it takes place easily. When the light is not present, okay, then also reaction takes place, but this step will be very slow. This is fastest step, because this hydrogen bond, right, this hydrogen and chlorine bond dissociates easily in presence of light. Light is nothing but photons, right? So we have photons here, and photons has certain energy, and that energy of photon we can define as E is equals to h nu, where nu is the frequency of the light, right? So actually, this much of energy provided by the photons to these reacting particles, and if it is sufficient energy we have, then bond dissociation takes place, and further the hydrogen and chlorine atom combines. If light is not present, then the reaction will be extremely slow, right? Hence, it enhances the rate of the reaction. But it is not a general thing, okay? It is only a factor where light we use for those kind of reactions. Those reactions only we have a factor of this. Otherwise, it is not a factor. Okay. The last factors which influence the rate of the reaction is temperature. Okay. And this particular point, temperature, we'll discuss in the next class. Okay. Because there are 2-3 things we have to discuss here. Here only we'll discuss also the concepts of activation energy, how temperature affects the rate of the reaction, Arrhenius equation we'll see. Okay, we'll see the graph also and the equation of it, rate constant and temperature equations. So there are 3-4 things we need to discuss in this temperature thing that we'll discuss in the next class. Okay, so write down this. So next class will start from this. You just remind me, so the temperature thing is left. We have to discuss it when I'll ask you in the next class. Okay, so basically this temperature fact, it depends upon whether the reaction is endothermic or exothermic, endo or exo. Based on this, the relation of rate constant and temperature we'll see in the next class. And then we can see whether the reaction is, it goes with a faster rate or slower rate, depending upon the value of K, whether it is increasing or decreasing as we regulate the temperature of the reaction. Okay, so those things we'll discuss next class. Okay, any doubt, guys?
No, sir.
No, sir.
Okay, thank you. We'll see you in the next class. Take care. Bye-bye.
Thank you, sir.
Bye, sir. Thank you.
Bye.
Thank you, sir.